The aim of the experiment is to study the EMF induced as a function of the velocity of the magnet. To measure the maximum velocity, the formula given on the screen is used. In this formula, R represents the radius of the semicircular wheel, which is actually the distance of the magnet from the point of suspension. The magnet is shown by black color bar and also pointed by an arrow on the screen. First, we have to calculate the time period which is required to calculate the maximum velocity. To calculate the time period, we first give oscillations to the wheel with a fixed value of theta and count the time required to complete 5, 10, 15 number of oscillations. In this way, we take at least 5 set of readings and calculate the time period by dividing total time taken with number of oscillations. On taking the average of these values, we have the average time period. Now, we have the values of R, which represents the wheel radius, T, the time period. By making the circuit mentioned on the screen and taking different values of theta. When the wheel oscillates, the magnet passes through the coil. The induced EMF is displayed on the screen of the voltmeter. Note the maximum induced EMF for different values of theta. Also calculate the maximum velocity from the formula mentioned on the screen for different values of theta. We now plot a graph between induced EMF and maximum velocity. The graph shows a linear behavior. The reason for linear behavior stems from Faraday's law, which states that the EMF induced in a coil is directly proportional to the magnitude of rate change of flux through the coil. Also, the rate of change of flux is directly proportional to the velocity of the magnet passing through the center of the coil. So, in the ideal case, plot of induced EMF with velocity of the magnet is expected to be linear. In this part, we will find a relation between induced EMF in the coil and number of pulses generated. We first make the circuit as shown on the screen. In this circuit, the diode plays a very important role. When the magnet enters the coil, a positive pulse is generated. But when it exits from the coil, a negative pulse is generated. The diode acts as forward biased for the positive pulse and reverse bias for the negative pulse. When diode is not used in the circuit, 4 pulses appear in one complete oscillation. The negative pulses cancel the effect of the positive pulses and no charge is stored in the capacitor. Hence, a diode is used in the circuit which filters the negative pulses and passes only the positive pulses. It means when a diode is connected in the circuit, one oscillation contains 2 pulses. Now, to find the relation between induced EMF and the number of pulses, we move the wheel with fixed value of theta and note induced EMF for 2, 4, 6, 8 and so on pulses. We take about 15 to 20 readings. A graph is plotted between the induced EMF and the number of pulses. The graph would tend to saturate after some time when the capacitor gets fully charged. In this part, we will find the relation between induced EMF and 1 by R, where R is resistance used in the circuit. We use the same circuit as mentioned in the last part and take different values of R, where R be the resistance. Now, to measure the induced EMF from the voltmeter for different values of R is the procedure for this part. About 5 to 8 readings are recorded. We then make a plot between the induced EMF and 1 by R. The graph shows saturation after some time when the capacitor gets fully charged. In this section, we will calculate the magnetic induction by using the formula as mentioned on the screen. For this experiment, we use the same circuit as mentioned in the previous parts and take about 5 to 6 different values of R being the resistance, and measure the induced EMF. The magnetic induction is then calculated. The values of magnetic induction are expected to be equal for different values of resistances because the same bar magnet is being used for all the measurements. This part includes analysis of electromagnetic damping. The damping will be measured for 4 different circuits. Number 1, open circuit, where only the coil is used. Number 2, short circuit, where terminal of the coil is shorted by a plain wire. Number 3, a resistance is connected in series with the coil. And number 4, a capacitor and diode are both connected in series with the coil. The graph on the screen simultaneously shows the damping for different circuits. It was found that maximum damping takes place in the short circuit case because it offers minimum resistance. So, large amount of current passes through the coil, generating large back EMF, and hence damping takes place.